So today I will continue with my course. Today I will look at the results of Gavrilyuk-Koolen, although I will start to look at the proof tomorrow. Today is mainly to get some of the tools ready. I'll enter today's talk with a conjecture that somebody can solve this in this workshop. Okay, so I will look into the characterization of the Grassmann graphs JQ2DD. These results are mainly due to Gavrilyuk and myself. We will also need some ideas of a paper of myself with Hayat and Rias, that is Hayat Sakander, myself, and Mohammed. And there's a spectral characterization of the S-clique extension of the square grid graph. And some of the arguments he Gavrilyuk could improve because he can simplify, because he knew our graph is the local graph and this the static graph. But essentially the same proof as we use for that paper we are using. Also, I want to mention another paper of mine. We may be able to improve the method. In this paper, we improved the method of Hayat, Rias, and myself. So it may give a slightly better bound on the diameter. But I did not look into this, whether it can really improve. Okay, let's really get started today. To prove that the Grassmann graphs JQ2DD are characterized by the parameters is much more different than for the other Grassmann graphs. One such problem is that we will be able to find enough delta cliques. Now we don't have that every delta clique, every edge is in one delta clique, but in two. So we cannot prove the graph is geometric, I think, until we know that the graph, it is a Grassmann graph. Then we know it is geometric, but I don't think that it is possible with the method we used to do it earlier. So I will introduce some tools I need for the proof. And I will enter some conjecture today. So I will first start with the result of Paul Terwilliger. This is fairly old result, I think in 1980s. So we start with an Israeli graph with distinct eigenvalues k, theta 1 up to theta d. And we assume that diameter at least 3. It also works for diameter equal to 2, but we are mainly today interested in diameter 3. Then any local graph, delta x of gamma, has smallest eigenvalue at least -1 minus b1 over theta 1 plus 1, and at most -1 minus b1 over theta d plus. So you can see that the eigenvalues, the second last, the eigenvalue is quite bounded for a local graph. The local graph at the vertex x is denoted by delta. And moreover, if the multiplicity f of the eigenvalue theta I is not equal to k, is less than k, then I must be in 1 or d. I must have that the corresponding -1 minus b1 over theta 1 plus 1 as an eigenvalue of delta x is at least k minus f. So we get that this eigenvalue gets the last multiplicity if f is sufficiently smaller than. So how do you prove this? This is not so difficult. It's essentially you use a standard representation. So you look at the vertex x of gamma and you look at the set of neighbors of x, and let delta x be the induced graph, subgraph on the gamma x, or on the neighbors. And let theta be an eigenvalue of gamma, and let ui be the standard sequence with respect to theta, and let sigma be the standard representation. Now we consider the symmetric k times k matrix Q indexed by the set gamma x, such that the UW entry is such an inner product sigma U, sigma W for any UW in gamma x. So this is so Q is clearly positive semi-definite, because it's in the gram matrix. Let B be the adjacent matrix of delta X. Then you can easily see that the matrix Q is I plus U1 times B. Every two vertices at distance 1 have in the standard sequence inner product U1 and plus U2 times J minus I minus B. And you can write that as U2J plus U1 minus U2B plus 1 minus U2. And we already said that Q is positive. So the graph delta X is one regular and hence has an eigenvector, the O1 vector. May assume that we have a basic of orthogonal eigenvectors of the graph delta X. And we may assume that the first eigenvector is all. And let eta be an eigenvalue of delta X with eigenvector X orthogonal to the O1 vector. So the sum of the entries of X is equal to 0, in other words. Okay, so now we can look at Q times X. That is U2J plus U1 minus U2B plus U1 minus U2 identity times X. And you can then write it as this because J times X is 0. So that gets cancelled out, and for B it has the eigenvalue eta, and for the identity, of course, it has eigenvalue 1. This means that U1 minus U2 times eta plus 1 minus U2 is greater or equal to 0, as Q is positive semi-definite, because all eigenvalues of Q must be positive, of at least non-negative. Using the formulas of the UIs, one can see that this is equivalent to eta is at least minus 1 minus B1 over theta plus 1 if theta is bigger than minus 1 and smaller or equal to this number if theta is smaller than minus 1. Now we know that theta 1 is at least 0 and theta d is at most minus square root of 2. And then we see the sharpest inequalities we get if theta is in these two values, theta 1 and theta d. This shows that any local graph delta X of gamma has eigenvalue at least minus 1 minus B1 over theta 1 plus 1. Second last eigenvalue at most minus 1 minus B1 over theta d. So we get the bounds on the local eigenvalue. We already have seen that the rank of Q is at most F because we can take M equal to F. So if F is less than K, then Q must have a 0 eigenvalue. From the above proof, you can see that then I must be in one of these, because then you have to have the sharpest inequality and multiplicity of minus 1 minus B1 over theta plus 1 as an eigenvalue of delta X is at least K minus F, because it's K minus the multiplicity. That is the rank of Q. So Q has order K is a K times K matrix and a rank at most F. So therefore, the 0 rank of the 0 eigenspace must be at least K minus F. This shows the. So now I will discuss the distance graph with classical parameters. Grassmann graphs have classical parameters, and many other distance graphs have classical parameters. It is a little bit complicated. So it's said to have classical parameters D, B, alpha, beta. Some person prefer instead of the being a small q, but let's stick with the B today. If the diameter of gamma is D and the intersection numbers of gamma can be expressed as follows. B1 is D over 1 minus I over 1 times beta minus alpha I over 1, and Ci is I choose 1 plus alpha I minus 1 choose 1, where I is between 1 and D. Where J choose 1 is the Gaussian coefficient. That means that J choose 1 is Bj minus 1, B minus 1 if B is not equal to 1, and just the binomial coefficient if B is equal to 1. So all the known infinite families of distance radial graph with valency at least 3 and with unbound diameter have classical parameters or are very closely related to an infinite family of distance radial graph with classical parameters like the folded Hardy cubes and the double Grassmann graph. So they are either they are themselves classical or they are somehow primitive. But the primitive subgraph, this primitive graph, if you have an antipodal graph, if you look at the folded graph, then that is has classical parameter. If always have a bipartite, then the half graph are having classical parameters. Important subproblem by nice problem which I discussed on the first day is to classify the distance graphs with classical parameters with large diameter. This is already a very hard problem as the twisted Grassmann graphs do exist. I think they are the most, on this moment, the most difficult problem, or maybe the quadratic force graphs or so, but I would think the twisted Grassmann graphs. So it is known that a distance radial graph gamma with classical parameters d, b, alpha, beta have that b is always an integer, not equal to 0 or -1. On the first day, I classified the one with the classical parameters with b is equal to 1. That you can at least the one with an quadrangle, because they will have the last eigenvalue equal to second last eigenvalue equal to b1 -1. If they have a quadrangle, then we have classified them. So this was, of course, what Terwilliger did maybe about 40 years ago. So if b is greater or equal to 1, then what is this? What did I make? Then b is really b1 over theta 1 plus 1. So you can write, so this means really that theta 1 is b. So then, I hope I did not make a mistake here, but so if b is 1, then you get that theta 1 is b1 -1. And if b is 2, you get that theta 1 is b1 over 2 -1, and so on. This is really correct, this formula. So for b is smaller or equal to -2, then they were more or less classified by Xu Wang. What do I mean by almost classified? He classified the non-bipartite graph with diameter at least 3 and obtained beside the known examples parameter family of feasible intersection. Until this moment, we don't know whether this two parameter family does exist or not exist. I don't think there's much progress in the last 20 years about this family. Maybe I'm wrong, maybe Paul knows more than I do. So what do we need for this talk? We need the following, for this course, we need the following consequences of the classical parameters. That k is d choose 1 times beta, a1 is beta plus alpha times d choose 1 minus 1, and c2 is b plus 1 times alpha plus 1. And moreover, we know that the small eigenvalue theta min satisfies minus d choose 1. This means that the order of a clique, the order C of a complete subgraph of a clique, we have C is at most beta plus 1, because that is essentially 1 plus k over d choose 1, and that is 1 plus beta. So therefore, beta has a combinatorial meaning. Similarly, the alpha has a combinatorial meaning. So if C is a delta clique, then a vertex outside C has either 0 or alpha plus 1 neighbors in C. So it's either alpha plus 1 or 0. I will need that we used yesterday in the characterization by Metsch. So From now on, we only consider distance-heading graphs gamma with classical parameters where b is at least an integer. And we will introduce the Terwilliger polynomial. That this polynomial always exists for a Q-polynomial distance-heading graph that is known, of which the family of classical parameters is a subclass, and the natural ordering for a distance-heading graph with classical parameters d, b, alpha, beta, where b is positive, the natural order of the eigenvalues is also a Q-polynomial order of the eigenvalues. So it's Q-polynomial and the natural order of the eigenvalues gives you Q-polynomial ordering. I will only discuss, but sometimes they have more than one ordering that can happen, but that happens only for b negative. One is positive and one is negative. So some classical parameters have two Q-polynomial orderings. You can write it as two different ways as a classical parameter. I will only discuss this Terwilliger polynomial for distance-heading graph with classical parameters, but it always exists when the graph is Q-polynomial. I'm sure that somebody already defined what is Q-polynomial. But if you don't know what is Q-polynomial, we just stick with classical parameters. That will be good. And for a detailed proof of its existence, there is a sketch of proof in the lecture note by Terwilliger as edited by Hiroshi Suzuki, but it is not exactly complete. So with such a Gavrilyuk, we found a detailed proof for it. It is in the paper, the Terwilliger polynomial of a Q-polynomial distance-heading graph and its application to pseudo-partition graph, and it's published in Linear Algebra and Application in 2015. So let gamma be a distance-heading graph with classical parameters, b, alpha, beta, with b at least an integer. Then there exists a polynomial pt of x of degrees 4, called the Terwilliger polynomial, so that for any eigenvalue eta of the local graph at a vertex. So I'm sorry, here's a misprint. It should be small x and not a big X. So delta x, the x should be small x, for any vertex x of gamma, with an eigenvector orthogonal to the R1 vector. We need that. We have that pt of eta is always greater or equal to 0. And the roots of pt correspond to the irreducible Tx models with n.1 that are 10. And I suppose that Paul introduced the Terwilliger algebra with a base point x. So that is the Terwilliger algebra. And I think that in the course of Terwilliger, you will see what the Terwilliger algebra is. So I will not introduce the Terwilliger algebra. So you have to use the Terwilliger algebra to prove that the existence of this polynomial. But that's all what I'm going to say of this polynomial. So, but it's very important that the local eigenvalues must have this pt eta is greater or equal to 0. All the eigenvalues eta which are not equal to a1 must have pt eta is at least 0. The proof for the characterization of Grassmann graphs tomorrow. So that is tomorrow I will consider the local graph, and then on Friday I will look how to use that to characterize the Grassmann graph. I want to say something that is also important tomorrow, but you will not see that yet. One of the steps should be that we have in our paper with Sascha Gavrilyuk should be done in a more general case. I will talk about that. I come back to this sort of things tomorrow. Don't worry. But for now, let's not worry about what it is significant. So I think it's on itself already interesting enough. So a co-edge regular graph with parameters VKC is a regular graph with 3 vertices. Valency K is regular with valency K, and any 2 non-isolated distinct vertices have exactly C common neighbors. So it's a generalization of strong and regular, because there you don't have that. Here you don't need to have that any 2 unchanged vertices must lie in a common neighbor. We also introduced the term of mu graph regular. It means that any mu graph has valency K prime. So what is a mu graph? The mu graph XY is the subgraph induced by the common neighbors of X and Y, where X and Y have distance to in gamma. And we say it is mu graph regular with parameter K prime if each mu graph is a K regular graph, K prime regular graph. It's easy to see that if a distance regular graph is mu graph regular with parameter K prime, then any local graph X of gamma is co-edge regular graph with parameters K, A1, K prime. So what you use is a local graph of the mu graph of local graph is a local graph of the mu graph. That is exactly what happens. That these 2 operations commute if you look at locality and the mu. So now I will introduce thin distance regular graphs. I'm not sure whether Paul already did this. So let gamma be a distance regular graph with diameter d at least 3. And for a fixed vertex x, let Tx be the Terwilliger algebra of gamma with base vertex x. And the graph gamma is called thin if for all x, all the irreducible Tx modules. So that means that all the dimensions are 1. So call 1 thin if it holds for all vertices and with n.1, all the irreducible Tx modules with n.1. Then it's called 1 thin. So now I will discuss a theorem and a conjecture. The theorem is by Terwilliger, although it's never, so it is in the lecture note by Terwilliger and as edited by Hiroshi Suzuki. I think it's 1993 or so, maybe 1994 that Hiroshi Suzuki was editing. Let gamma be in thin Q-polynomial distance regular graphs. And if you don't know what Q-polynomial, think about distance regular graph with classical parameters with diameter at least 5. Gamma is mu graph regular. In his theorem, he can show many more combinatorial regularities of the graph gamma, but I will not going to discuss what he did more in that theorem 77 in that lecture notes. So the conjecture is you can replace thin by 1 thin. This is true. That will be very helpful for my characterization tomorrow. It's not so difficult to prove it. So what I observe is that proof of thin Q-polynomial distance regular graph should also work, what is in those lecture notes, should also work for the 1 thin Q-polynomial distance regular graph, except for one problem, but I discussed this small problem with Professor Ito, and he told me that what I thought is correct. That is correct. So what he said, the only problems that need to be solved is that the irreducible Tx borders with n.2 are sharp for Q-polynomial distance regular graph. It's sharp. That means that E2 star xw, the dimension of that vector space is 1 for any irreducible Tx module W with n.2 for any vertex. Correct? If I understand Professor Ito correctly, then this should follow by the Ito-Terwilliger theory of the 3 diagonal pairs. So tomorrow I will start with a proof of the characterization of J2DD, but it's here where I stop for today. Thank you.
Thank you. Go ahead. No, go ahead. So are you saying, Jack, that you have that mu graph regular
theorem if you assume that all modules of endpoint 1 are thin and all modules of endpoint 2 are sharp? Both, then the theorem is already proven?
I think the theorem is not proven on this moment, but I think all the steps are in the lecture notes by Terwilliger, except for that sharpness. That is what you need. You need some bijection between two spaces.
Okay.
That
So
is the rest will work as it is in that. Of course, it is not so trivial to see all that everything will work like that, but I checked it and it looks like it will all work. So the details I don't know, but maybe somebody in that workshop can figure out all the details.
yeah, I can, let me just add my 2 cents. So I agree with Ito that the irreducible T modules with endpoint 2 are going to be sharp. But that is correct.
So then the rest is also correct.
Okay, yeah, and more than that, it's not just endpoint 2 in the.
I think for the 3 diagonal pairs, it's always sharp because
it's always sharp for this.
Because algebraic closed field, if I'm correct.
Yeah, that's correct. Yeah, and I
agree that one of you can write a paper about it and helpful.
Yeah, sir. Yeah, I apologize for being so slow about writing up some of the items from those Suzuki notes.
It's only been 26 years.
Notes for this my notes for this workshop were a belated attempt to write up, type up some of that. So I agree also that for that mu regularity, if you just need one thin. I agree that should be true. You just need one thin instead of all of thin.
Yes, I think so. So I checked, and it looks like you only need one thin. Yes.
I have another question. So Jack, can you go back pretty early in your slide? So you taught me about this parabola. This is very important parabola, and I'm trying to find it in DCL during your talk. And
so I will put it on the where do you want to go?
Pretty early in your talk, when you introduce, when theta, you have,
first
B1 over theta plus 1, right? The very first time you have this. So here, so you have second smallest eigenvalue that leaves this. So this parabola is a very important thing. So on the next slide, or somewhere, you delete the subscripts, and I don't know which theta you mean. So coming up very soon.
Oh, I meant here gamma x.
Okay.
I mean, the local graph. This delta x is a local graph at vertex x.
Okay, yeah. So I'm interested in.
I'm very sorry for the confusion.
No. I'm interested in something else. Can we go further forward?
Next one.
No, I'm looking at the B1 over theta plus 1. Look, this ratio, B1 over theta plus 1. Yeah.
Yes.
Okay. Yeah, that's okay. I understand that. Okay, now continue forward, please.
The proof.
Yeah, maybe the next result where that shows up again. So, yeah,
this
here.
One?
Yeah. So which theta is that?
So that's an eigenvalue for the original graph.
So theta is the eigenvalue original graph, and eta is the eigenvalue for local graph.
So theta, if theta is greater than -1, then eta
is greater equal to this.
This.
Because yeah, you have to worry about a negative sign. That is what happens.
Dividing by a negative, the sign flips. Is that what?
That's all happens here.
So you're dividing by theta plus 1, and that's why the sign flips. This is true for any eigenvalue theta?
So it works there for the second largest and the smallest eigenvalue. That gives the best bounds for eta.
Right, I'm used to seeing it for the second largest and smallest. I wondered.
That's just because the other eigenvalues don't give you any extra information.
Right, so I'm used to just seeing it for the second largest and the smallest. I was confused with the lack of subscript. Now I see that it's true for any any particular eigenvalue, any chosen eigenvalue.
But for theta not equal to the second largest and the smallest eigenvalue, that gives you worst bounds on eta.
And theta's not the valence, right? Theta's any eigenvalue, including the valence?
No, not the valence.
Not the valence. It's any non-trivial eigenvalue. Okay, thank you.
Any other?
Can I ask?
Yeah, Jane.
Hi, Professor Koolen. I have a question about the Terwilliger polynomials. So, is there any combinatorial interpretation of that polynomial?
I let Paul answer this question, please.
I think of it as more of an algebraic thing. Somehow you have this degree 4 polynomial who's in an argument eta, let's say, and we think of eta as a potential eigenvalue for the local graph, and the 4 roots of that polynomial correspond to the eigenvalues of the local graph that you get from a thin irreducible module of n.1. So if you have a thin irreducible module of n.1, you look at the call it W, you look at E1 star W, so in other words, the intersection of W with the first subconstituent. Okay, so that'll be an eigenspace for the first subconstituent, the adjacency matrix for the first subconstituent. And that root, that eta, will be an eigenvalue. And so you can spot the thin irreducible D modules by looking at the roots of this Terwilliger polynomial. The strength of the real reason for looking at that polynomial is that you imagine the graph of the polynomial. Okay, 4th degree, so it's going to bounce around. So the intersections with the x-axis, those are the roots, of course. The polynomial, the graph of the polynomial has to be above sea level, above the x-axis, at every eigenvalue for the local graph. So, wherever the graph goes below the x-axis, in that interval, there are no eigenvalues for the local graphs.
There's at most 4 local eigenspaces that can be the beginning of 2 models at point 1.
There are thin.
Right.
So all the other eigenvalues will correspond to the beginnings of some irreducible T module, but it's not going to be thin unless you're at a root.
Right, those are the 2 ones. Okay.
Question about the Terwilliger polynomial as well.
Yeah.
So in this, in Jack's lecture now, it was just to find the classical parameters.
Yeah, he's just sticking to that case.
So if you weaken this and say any distance variable graph,
But it's got to be Q-polynomial.
okay, any Q-polynomial, and you still.
So that is unknown on this moment, and it's very interesting question what it will work, what happens for a distance value graph.
Okay.
Interesting to
So we don't know if that exists.
how you can generalize this.
So so Jack, you're talking about the non-Q-polynomial, distance regular but not Q-polynomial.
Yes, it will be still very interesting to have this kind of polynomial for general distance radicals and not only for Q-polynomial ones.
Yeah.
But it's nothing's known about this stuff.
Well, so I have heavily used the Q-polynomial feature to get my polynomial. I mean, actually, I don't think there's going to be a 4th degree polynomial.
So maybe higher degree.
But possibly in general. But anyway.
Maybe it's not bounded the number of eigenvalues, for example.
Yeah. So it won't. So if once you get away from Q polynomial, there's no reason to think that the analog of the Terwilliger polynomial is going to be degree 4. So it's going to surely going to be some higher degree.
Yeah.
But anyway, the classical parameters part was not important. So for any Q polynomial, DRG, you have this Terwilliger polynomial.
But I will only need it for the classical parameters tomorrow. So therefore,
Yeah, understand.
Because for classical parameters, the roots are much easier to find than for Q-polynomial in general.
Yeah, that's right. So things, the whole theory simplifies quite a bit if you restrict to classical parameters. So for classical parameters, I'm sure Jack will do it. You can write down very quickly what the roots, what those four roots are in terms of the original alpha beta data. And there are closed form formulas for the roots for the general Q-polynomial case, but they're quite a bit more complicated.
But for generic Q-polynomial distance algebraic level, the Terwilliger algebraic could be parameterized, not classical parameter, but just Bannai parameters like R1, R2. From
Leonard's theory. That's you're talking about Leonard's theory. So
yeah.
So for the general Q-polynomial BRG parts, according to Leonard's theory, you can write down explicitly what are the intersection numbers, the BICI, eigenvalues, dual eigenvalues, everything.
But the polynomial looks very complicated.
So you write down a polynomial. Everything about it is order of magnitude more complicated in the general case compared to the classical parameters case.
No, I'm here. Don't worry.
There you are. Okay. All right. Well, thank you. Thank you.
Okay. Thank you. Have a good evening because I'm going to leave. Sorry.
Okay.